In this video, we're going to look at gravimetric analysis. Now, you've already done some volumetric analysis, which is when we use the volumes of liquids and things to work out how much of something we have. And now we're going to look at gravimetric analysis, which is when we use the mass or the weight. And this is another important quantitative technique. In this lesson, three main things that we want to learn to do. Firstly, describe how gravimetric analysis is conducted. So how do we actually do it? Secondly, to process the data from a gravimetric analysis. And thirdly, to evaluate and improve, if we can, validity, accuracy, and reliability. It's a good chance to revise those three things. So let's look at this. What is gravimetric analysis? It's a general term, so there are different methods used, but gravimetric analysis is a general term for finding the composition of a substance by measuring mass. And we use this method when we have a mixture of different substances and we need to find the amount or concentration of one particular substance in the mixture. So I've got three examples there: sugar in a muesli bar, a particular ion in a water sample, like how much lead is in the water, and sulfate in fertilizer. And these second two often come up whether they're in the old syllabus, they often come up in questions. And sulfate in fertilizer is a good one because plants need ammonia, and the ammonia is often there as ammonium sulfate, which plants need sulfur as well. And if you can find how much sulfate is in there, you often know how much ammonium is in there as well. Now, how do we actually do it? A few steps, but pretty much every time we do it, you're going to be weighing the original sample first so that you know the total mass of the whole thing, and we want to do this accurately. Then we're going to have to separate out the component that we're analyzing, and then we'll reweigh either the bit we've separated, or you could weigh the original sample without that component. Either one will allow you to do it. But pretty much every one we do will have those three things. We'll weigh, then we'll separate, then we'll reweigh. And that allows you to work out percentage composition, which is how we'll normally express it. Now, I've got three examples, starting with easy and going through to harder. First one, a simple one. If we wanted to determine the moisture of something, like a food product or soil, well, you could weigh it, and then you could remove the moisture by heating it to dry it, or by putting it in a desiccator until it's not losing any more weight, and then you reweigh it, and the difference will show you how much water is in there. And so you could work out the percentage water as a percentage of the original sample that you had. So there's a simple example of a gravimetric analysis, and it is based on mass. That's what we're using. A second example, lead in water. How would we do this? Because the water is liquid, the lead's there dissolved. How can we use the mass? Well, the key is going to be, how do we separate the lead? And you can do that through precipitation. So the same basic process: weigh your water sample very accurately. Then we could separate the lead through precipitation. So add something like iodide ions, chloride ions, something that will form a precipitate. Then you could filter it to get that lead iodide, dry it, and then weigh that lead iodide, and you could work out exactly how much lead was in your original sample. Although keep in mind that we would be getting lead iodide, so you would need to work out, hang on, how much lead is actually in the lead iodide. So there'll be a few calculations. Third example, and this is a common one as well, to find sulfate in fertilizer, same basic process. You would weigh your fertilizer sample. We're going to have to dissolve it in water. Then we can precipitate out the sulfate. Now, how do we precipitate it out? Well, you've learned that barium sulfate is insoluble. That was one of our tests for barium. So a typical way this could be done would be to add barium so that barium sulfate forms. Then we can filter that out and weigh the barium sulfate, and we work out how much sulfate is in the fertilizer. This is just the same process, but with a bit more detail. Okay, we accurately weigh it. How do we add barium ions? Well, nitrates are soluble, so we could add barium nitrate, and we would make sure we add excess. So make sure we get all our sulfate precipitated, and then we can dry it properly and weigh it. There's a little note there. Often we add acid as well when we're dissolving our fertilizer, and the presence of the acid can stop other substances from precipitating. It makes some of the carbonates and things like that, like carbonates will react with the acid, so they're not a problem anymore. It can make it more accurate. You'll only have the sulfate as your precipitate. So that's the basic process. There are a few little tricks for this one. barium sulfate is very fine, and often some of it can pass through normal filter paper. So if we were doing this, a laboratory technique that's used here and in other places is to use a sintered glass filter, and it is actually made of fine glass that's sort of joined together in a process called sintering, and that gives a much finer filter so that you can filter things like barium sulfate. Because it's going to be then very slow to get through, we often use suction, and so you try to create a lower air pressure inside your flask to draw the moisture through. And you can see in the diagram there's a rubber hose joined to the side of the Buchner flask, and that will be drawing air through, which causes your solution to go through much faster. So they're little laboratory techniques. You won't be asked directly about them. It's extension, but helpful little chemistry things to be aware of. So that's the basic process. We weigh our whole sample, we separate one component, often through precipitation, and then we reweigh or weigh that component that we managed to extract, and we can work out the percentage composition. So what calculations do we need to do? Well, the long way, which I'm not going to get you to do, if you've got something like lead iodide, right? You've got your precipitate from your water sample, you've precipitated out the lead. You could work out how many moles of lead iodide do we have from your mass. So then you can work out the moles of lead. So then you can work out the mass of lead, and you can work out the percentage. There is a shortcut we can do to avoid having to do all those calculations. Instead of doing all of that, we could replace those first three steps with this. We know the proportion of lead in lead iodide. So if you take a substance like lead iodide, you can work out the molar mass of lead iodide just by adding up one lead atom and two iodide atoms, because it's PbI2. So you know the molar mass of the lead iodide, and you know the molar mass of lead. So you can work out what proportion or percentage of the lead iodide is lead. And so we can come up with a simple little formula like this. If you know your mass of lead iodide, the mass of lead is just the molar mass of the lead divided by the molar mass of lead iodide times your mass of lead iodide. Right? It's just a ratio. How much of the lead iodide is lead? You multiply that by the mass of lead iodide. So that's a much simpler way to do it if you can follow that. And then you can work out what percentage that lead is of the entire sample. And that's pretty much it for the calculations. They can throw in dilutions as well, and it could be part of other reactions that occur, but the basic calculation is actually quite simple. A little note on units. I'm not going to go through all of this. We did it in year 11, and at the bottom there you can see a link. But just be aware that when we're measuring very small amounts of things like this, often we record it in ppm, parts per million. So you do need to be able to work in parts per million if required. And I've put there how to work it out, but I won't go through it now. But basically 1 ppm means 1 milligram per kilogram. And because a litre of water is a kilogram, 1 milligram per litre is 1 ppm. Finally, validity, accuracy, and reliability. This is a good chance to revise some of these things. It's worth knowing basic definitions. Like validity, are we measuring what we intend to? If we want to measure the amount of sulfate in fertilizer, is our procedure actually measuring that? Accuracy, is our value close to the true value? And reliability, do we obtain consistent results? So what would that look like for gravimetric analysis? Validity, one of the key things is, if we're using precipitation, are we only getting the ions that we want when we form the precipitate? If other precipitates are forming, then it's not really going to be valid. And then are we drying it properly? Because if we don't and there's still water there, we're going to have the mass of the water affecting things, and that won't be valid. It affects accuracy, but so much that it's invalid. Our accuracy, well, we're going to use volumetric glassware if we're measuring solutions. We're going to use an electronic balance, and we want that to be very accurate. And then we can compare our value to the manufacturer's claims. So this is an example of where we know the supposed true value, and we can compare. And finally, reliability. We do want to repeat to see if there's consistency. And I've just got a table here that helps you see some examples of how, if your procedure is not done well, then it will introduce errors, inaccuracies, and it can undermine the validity. Like the first row there, if you don't get complete precipitation and you leave some of the substance behind that you're trying to test, you're going to get an underestimate. Your value will be too low. If you lose some of your precipitate in transferring, right? Some of it goes through the filter paper and you don't have it captured, again, your value will be too low. Other things could be causing the value to be too high. If you don't dry your precipitate properly and you've got moisture there, your measured weight will be too high, the mass, and you'll get an overestimate of your value. Or if there are other things that precipitate, your final mass of your component will be too high, and it will give your final value will be too high as a percentage. So that just helps you see this is a good example of how the procedure will affect the validity, whether we're actually measuring what we want to, and the accuracy of that final value. And they could ask you in an exam, it would be a good question to think about. A particular process happened and the value was too high, what might have caused that to happen? Or a particular process was followed and this is how they did it and what happened? Would you expect the value to be too high or too low and why? That would test if you understand these things. That's all on the questions, the activities that you'll do during the lesson. We'll just revise the procedure for gravimetric analysis, the calculations, and then validity, accuracy, and reliability.